Welcome to Physics 210 online. Today we're going to start one of our first online classes, and we're going to start with this discussion of magnetic flux. Okay, let's start by drawing a surface. Here is a surface here, right? It's not a closed surface by any means, it's an open surface, so stuff flows through it. So let's imagine I have some B field that moves through this thing. So there's my surface S, and I have some B field that goes through the surface here. Right, and consider a point here which has a normal vector associated with it, which I shall call n hat. All right, so I got locked. Hold on, lock it, locked it. Autofocus. It's not locked. Locked incorrectly. Focus, lock. Oh, jeez, it's doing that. All right, so it's locked now. Okay. All right. So to define my magnetic flux, phi sub m is equal to the integral over my surface S of B dot dA. Okay, where this area has a vector above it, and what that corresponds to is basically integral of B dot n hat dA. Right, so dA is equal to n hat dA. All right. Okay. Now, if basically well, let's see. So let me write this down. So this is the flux, right? And so it depends on basically what the local B field is at any particular point as it passes through this flux, right? And the normal to the surface. So for instance, the B field is this way, basically you have some flux. If on the other hand the B field is like this and N hat's like that, okay? It's orthogonal 90 degrees. So in this case, basically the flux is 0, right? So this is phi of m equals 0. All right. Now let's consider well, let's discuss the units of flux. Sorry. So the unit flux is, well, let's go think about this very carefully. So this is going to be basically going to be 1 Tesla meter squared, right? Because that's the area, that's the B field, and that's equal to 1 Weber, right? Which is short WB. Okay. All right. Let's consider the simplest thing, right? So for uniform B and a flat surface, all right, then what we have is basically suppose I have some area A here, and I have some B field going through, right? Then basically integral of B dot n hat dA. Now in that case, basically uniform B means this is constant, and the flat surface means this is constant. That's simply going to be equal to basically B sub n A, right? Where this is just B dot n hat, right? So that's just the magnitude of the B field in the direction of the normal. Okay, now why do we care about magnetic flux? Well, here's a critical thing. Changes in magnetic flux, whoops, right, induce changes in the EMF along the path, and what it means is really the boundary of surface. Okay, all right, so let's draw a picture of what this looks like. So if I have my B field and this goes along some surface S, right? If this thing changes, if the magnetic flux changes, right, then what will happen is that this will induce an EMF that goes in this direction, right? Okay, we're going to talk about this a little more closely, a little more carefully in a second. All right, so the EMF is going to be equal to minus d phi m dt, which is equal to minus the integral c e dot dl, right? Where the c is this curve going around this thing. All right. Now, what does I want to say? So one thing you've noticed is that I wrote this little m there, and that's because this is distinguished from the electric flux, which is in Gauss's law. All right. Okay. So that's the magnetic flux. Okay. Let's go talk a little about. Let's give an example of that. So as an example, all right. Okay. All right. Suppose. Okay. Pause the recording for a second. Pause it. All right. Back there. So, suppose you have a loop of wire, all right, and phi sub m through that wire is equal to 0.1 t square Webers, all right. Okay, suppose you have something like that, all right. What I want to find basically what is the induced EMF. All right, so that would simply be epsilon is equal to minus d phi sub m dt, all right, which is going to be equal to basically 0.1 d by dt of t squared, which is 0.2 t, and let's put on the right units, volts. All right, I'll write that thing down so it's not like you get confused or anything like that. All right, so that is our starting point. Let me pause for a second to try something. Okay, let's just have to change the lighting. Okay, so let's talk about the change in the flux. So the change in flux can happen in several ways. Okay, so the first thing is changing B fields. Second way is changing orientations. So first case basically the B field can change. Second way is the n hat vector can change, or the surface changes. And number three, changing the area. Okay, so let's do the first one, right? Changing B field. Okay. Now suppose B as a function of t is equal to 0.1 t squared Tesla in the x direction. Okay, that's terrible. It looks terrible. Okay. All right, so let's draw this thing out. I have there's my B field here. Okay, there's my surface here. I'll call this surface A. And A, I'm going to tell it basically is equal to 1 meter squared. Right. Okay. So once I have that, all right, I can just go ahead and compute this thing out. So phi sub m is equal to integral of B dot dA Well, what's that? Well, that's just going to be basically B times A, right? Because all the normal of this thing is the next direction, the B field is along the next direction. So this is simply going to be basically 0.1 t squared, right, times 1 meter squared. So 0.1 t squared Webers. All right. Okay, that's the part one. Okay, so the second part now. Let's now look at. Let's get the EMF. EMF is equal to minus d phi m dt, which is going to be equal to basically d by dt of 0.1 t squared Webers. That's 0.2 t, and the units of EMF, sorry, with minus sign, volts. Okay, perfect. I'm going to pause again and see if I can. All right, and we're back. Okay, just zoomed in a little bit just to get it perfect. Okay. Okay, so the next one, part two, is changing orientation. That's this piece right there. Let's talk about that. So, two, changing orientation. All right, so let's do this. So let's consider basically I have my B field along this direction. So I'm going to write B is 0.1 Tesla in the x-axis direction. There's my B field there, happily. Okay, and what I have here, this is the first significant thing that is interesting here. I have my my surface, and this thing has an axis of rotation. It's going to spin around like this, all right? So it's going to spin around with some frequency, angular frequency omega. Okay, and so the normal vector will be pointing in this direction, n hat will go like x hat cosine omega t plus y hat sine omega t. Right? So those are the two directions, all right? And so now we can basically do b dot n hat, which will be useful in a second, right? That's just going to be 0.1 x hat times x hat cosine omega t plus 0.1 x hat dotted with y hat sine omega t. All right. Okay, so x hat dot y hat, that goes to 0. X hat dot x hat, this goes to 1. Right. So that's just basically 0.1 cosine omega t. Okay. So once we have this, we can go ahead and plug it in, right? So phi sub m is just b of a, bn of a, right? So that's bn, that's b sub n. And so what we have, I should give you an area of this thing. Let you know that this area A is equal to 1 meter squared, right? So that's just going to be 0.1 cosine omega t times 1 meter squared, 0.1 cosine omega t Webers. All right. All right. So now we're done up to that point here. Okay. Now we can compute the EMF. This is EMF is equal to minus d phi sub m dt, and that's just going to be d by dt of 0.1 cosine omega t, which is just going to be equal to with minus sign, minus a minus is a plus 0.1 omega sine omega t. Right? And there we go. All right. Okay. Now, what's interesting about this is that if you notice it, because of the sine omega t, right, this thing will change. EMF will change sine as it rotates around. Okay, now I'm going to do one last thing, which is changing the area. Number 3. So the last one was changing area. Let's talk about that. Changing area. All right. So to do this, right, we're going to consider the following. Okay. So I have a rail. I have another rail like this. All right. To make this work, I'll have to put a resistor there. Okay. And what I'm going to do is I'm going to basically put a short circuit thing, a short circuit bar on this thing. And this bar is going to move with some velocity v. And there's going to be some B field everywhere. So I'm basically put some B field everywhere. This is the B field pointing into the page. All right. Okay, and I'm going to tell you what the B field is, because the B field is going to be minus 0.1 z hat in Tesla. All right, so just let you know, basically, the z hat is pointing up away from the page, so minus z hat is pointing into the page. All right. Okay, so this is the area that we're going to be concerned about, right? And so what this is going to be basically some length, all right, and some width, which I'll call x of t, all right? So if we go ahead and compute this thing, phi sub m is equal to integral of b dot dA, right? This is going to be equal to, let's get that's right, 0.1 times the area, which is going to be 0.1 times the length times the width, x of t. All right. Okay. Now I haven't told you what the 0 point is, because that's not really relevant. All right. I'll show you what this turns out to be. Okay. So if I go ahead and compute this thing now, EMF is equal to minus d phi m dt. That's going to be equal to minus d by dt of 0.1 times the length times x of t. So that's a constant, that's a constant, that is not a constant. This thing will just act on that. So it's going to be 0.1 the length dx dt. And what's dx dt? Well, that's just the velocity v. So this is just v, right? And so basically we're left with 0.1 minus lv. Okay? Or in other words, the absolute value of the EMF is 0.1 lv. Okay? These are fine. All right. Now let's discuss something called Lenz's law, right? And Lenz's law is important because it tells you what direction the EMF is going to be in. Lenz's law. Okay, sorry. Lenz's law. All right. Okay, so here's what Lenz's law says. It says that direction of the EMF, right, is to oppose the changing flux. Okay, so that's why, hence the minus sign. The minus sign, which minus sign are you talking about? Well, I'm talking about this minus sign right here. So that minus sign right there. Okay. All right. So let's go think about this. So suppose that you have a some B field here, and then you have some surface, right? Now suppose basically I'm going from 4 B field lines to 3 field lines. So it's getting weaker, right? Okay. Now, what Lenz's law tells you is that the induced EMF must be in such a way to oppose the change, right? So basically, it wants to induce a new B field line that's in that direction, right? Okay. So in order to figure out basically what direction that is, well, okay, so I need to get that. Let's go figure out what that is. So in order to do that, I have to basically just try out. So let's see. So if I use the right hand rule, so you basically point direction of the EMF or direction of current flow, and this will cause it to curl this way. So that's one way, two, third branch, fourth branch. Okay. So the EMF goes this way, that way, that way, and that way. Because if you force a current to go in this direction, you induce a new B field that moves in that direction. So that's the direction of the EMF. So this is now the direction of EMF. All right? Okay. So so basically, like I said again, direction of EMF drives current that opposes the change. Okay. So similarly, you could draw something else. So suppose you have 3 lines right here. And there's your surface again. Okay. And this is going to increase the 4 lines now. Okay, so I'm going to increase the 4 lines. 1, 2, 3, 4. All right. Then what I'm going to do is I need to do an EMF that basically opposes. I want to drive a B field in this direction now. All right. So to do that, we can use the right hand rule again. So let's do this way. So that points back that way. This points into the page. That points away. That points away. So it goes in hold on, make sure this is right. So I need it to go that way. 1, yeah. Whoops. 2, 3, and 4. Right. So that's basically a positive change in this case. All right, and we're back. Okay, so let's look to my notes here. Okay, so the first useful thing about this we're going to talk about is magnetic drag. Okay, so what I have here is that I have my little rail again. I'm putting my resistor here. I'm actually going to put some numbers here. So this is going to be some R. Okay, well, not R, but let's put some symbols here. And this length is L, right? And I have my bar here sitting on some frictionless tracks, bar mass M. I'm going to give a kick, basically a V0, right? And now what I have here then is I have some B field. Okay. All right, so I want to find, this is basically, let's find V as a function of T. All right. Okay, so let's get this right. All right, so the first thing I need to know is that the force that I'm going to experience, well, that's just basically I L cross B, right? Which in this case is going to be something of the order basically I L B, okay? And it's going to come in with the minus sign here, right? Okay, so what's I? I is just the driven EMF that I'm going to get divided by the resistor, right? And so what's that? It's going to be LV over R. Okay, this is something we just computed earlier, right? So then what that gives me is that the force is equal to let's plug that in for this piece right here. Minus B L V over R, okay, times, second part, L times B again, right? And this is ultimately equal to the mass times acceleration, which is mass dv dt. All right, okay, so now we can go ahead and do this thing now. Okay, so let's basically write this thing down. M dv dt is equal to, let's basically multiply everything together then. That's just going to be minus b squared L squared over R, okay, times V, all right? And so what this gives you, right, is that this is equal to basically dv dt, so divide by m now, is equal to minus b squared L squared over mr times v, right? And then you have to go ahead and solve this thing, right? So in order to solve this thing, all right, what I need to do is you have to use the trick, okay? So the trick is the following, okay? So we have to do the guess and check trick, okay? So the form of the equation looks something like that, okay? Which means you could write it as basically dv dt is equal to minus, I'll call this thing alpha v. Alpha is equal to b squared L squared over mr. Okay, this alpha just makes it more generic. You use it for anything then, basically. Okay, so now this is basically guess and check. The guess is basically v is equal to some amplitude exponent. I'll call this I call this basically anything I want, but I'll call this omega t. Okay. Usually I like alpha here, but I used alpha just a second ago. So, okay, so then we just, that's the guess. Guess. Now the check part, plug in. So d by dt of basically a exponent omega t is equal to minus alpha v, which is just a exponent omega t. All right, so this piece just brings on omega a exponent omega t is equal to minus alpha a exponent omega t, and it worked out. That cancels that, that cancels this, and so you have alpha omega equals minus alpha, which is b squared L squared over mr, right? Just from there. Okay, so we just plug everything in. So v is equal to a exponent minus b squared L squared over mr times t. And now we need the final piece of information, which is what is this velocity at t equals 0 is. Right? So let's go back. The velocity at t equals was v0. I probably said that. So v at t equals 0 is v0. Okay. So plug that in. So v at t equals 0 is equal to, you plug a 0 in here, that's 0 times that, exponent of 0 is 1. That's a, which we also know is equal to v0. And so now we're done. V is equal to v0 exponent minus b squared L squared over mr times t. And that's it. Okay. All right. So now, basically, that's kind of neat. All right. Now let's do something else. All right. Okay. So if I want to, well, okay. So let me just try pull this thing back. Okay. So if I want this object here to move at a, say, constant velocity now. Let's see, where's my note here? Here it is. if I want this thing to move at a constant, I just need to pull it with a certain velocity, right? So if I want it to move at a constant velocity v0, right, I need to pull it with a force. What's that force? Well, let's go back at that. That's the force right there, but with v equals v0. So I need to pull it with force. F is equal to b squared L squared over r, right, times v0. Okay, if I want to move it at constant velocity, okay, in x direction. Okay, so let's do basically one final example. All right, suppose I give you the force, and then you get determine terminal velocity. All right, so here's the following problem. Okay, so now I have basically this thing is falling now. Put a resistor across that. Put that down now. I'm going to put a mass across it. Has a certain mass, and it's being pulled with force equals mg. All right. Okay. So now, we want to figure out what the terminal velocity is. Right. That's when basically the F net equals 0. And so what are the forces here? So there's going to be a force of gravity pulling down this way. There's going to also be a force, a magnetic force pulling up that way, right? And that magnetic force is something we just determined. That's just going to equal to B, that's L again, squared L squared over R, put the R back again, right, times V, that's the velocity doing this way. That's going to have to be equal to basically mg, right? And so that gives me a terminal velocity. V terminal is equal to mg r over b squared L squared. Right? So it keeps falling until it hits this terminal velocity, basically, and then we'll slide down at constant velocity. Okay. So let me pause it for. Okay, and we're back. All right. So I'm going to talk about a new subject now, or not new subject, similar subject, inductance. All right. So recall that the flux is phi sub n is equal to integral of b dot n hat dA. Okay, so that's the flux. All right. Now for a coil, B is equal to mu 0 I over 4 pi r squared in the center. I don't remember that. Let me check that. Okay, so hold on, let me just correct. This is not right. So this is for coil. A coil is like this. Okay, the B field is equal to mu 0 I over 2r. Okay. Okay, in the center, right now. Okay, so let's see what I say. Okay. Now, what's interesting about this is that the field can vary by a bit, okay, from place to place, but it's always proportional to I. Okay, so B field is proportional to I, right? It's very much like capacitors, where basically the voltage drop was always proportional to Q, right? In this case, basically the B field is going to be proportional to I. All right. Now, for solenoid, right? So you basically have a solenoid we can describe as object here that is of length L with n turns or n coils, right? And in that case, B is equal to mu 0 n times I, where n is capital N over L, right? Okay, so the flux phi sub m, well, that's just basically how many coils we have. We have n coils. What's the B field we have? We have B fields, and we have A. So it's the NBA, all right? Okay. So that's just going to be equal to, basically, if you plug this thing in, so that's going to be mu 0, right? N over L, right? Times the, let's see, so that's, I need another N here, okay? NL times I times A pi R squared, okay? So that's A, that's B, and that's N, right? Okay? And so, this again is only just proportional to I. We can just simplify this a little bit. Mu 0 N squared over L pi R squared times I. Okay? So again, proportional to I. Right? So, what's interesting is that this stuff out here, right? This is related to the flux. This is some object here, right? And so what we can do, we can define phi sub m is equal to L times I, so that L is equal to phi sub m over I, very similar to basically what we did for capacitance, which is the voltage divided by Q, right? Okay. And so what we have is that basically, so L is called the inductance, right? Okay. And units are Webers over, amps, amperes, current, right? So that's called something called a Henry. Whoops. Henry. All right. Okay. So this is basically important. So this is this is important for devices known as inductors, right? In a circuit where d phi m dt is equal to d Li dt, so this is EMF, is L di dt is the EMF due to changing currents. All right. Perfect. Okay. Okay. So, let's get that right. So this is going to be equal to minus, minus, and minus. All right. Okay. So let's see what I want to say here. All right. So so I'm gonna write one. Let me think. It's not gonna be important. Okay. Let's do this thing. Okay. So all right. So I have this EMF now. The EMF is equal to minus L di dt. So this is EMF due to inductors in a circuit now, right? So in a circuit, let me just think about this. Okay, so in a circuit, inductors are represented by a symbol. This is a symbol. Looks like a squirrely thing. It's just a bunch of coils busy together, right? And the potential drop is basically minus L di dt. All right. Okay. Potential drop in the direction of current flow. Okay. So let's start by considering some circuits. Okay, so I'm going to do the following circuit here. Here is my circuit here. I'm going to have some voltage source. I'm going to open up the current for a second, open up the circuit for a second, put a resistor in there. Now put my inductor in there and close everything up. Right? My inductor has inductance L, my resistor has resistance I. There will be some current flowing in this direction, I. Okay? So at t equals 0, I flip the switch. So this thing comes down, completes the circuit, right? And now basically I have to figure out what this thing looks like. Okay, so let's go around the circuit. Okay, we're going to use Kirchhoff's law, right? And so as we go around, we're going to go across this thing. So this gives me a plus V. Okay, going across the resistor, it gives me a minus IR. Come back down, go across the inductor, right? And the inductor has a potential drop in the direction of current flow of minus L di dt. So minus L di dt. And then I complete everything, that goes back to 0 now. Alright, so now I have to go and figure out basically what this thing looks like. Alright, so in order to do that, what I'm going to do is that I will solve this equation, right? So we're going to solve this thing. So need to solve. Okay, and this one you just can't guess and check, or you have to make an important substitution. So here's substitution I'm going to do. I'm going to basically let U equals V over R minus I. Okay, so you see if I divide by R here, this thing here becomes U, and then du is equal to minus d or u dt minus di dt. Okay, so let's go ahead and basically work this thing out. So this is going to be equal to u minus, all right, this piece here is just going to be plus L over R du dt, right? Okay. Or in other words, basically, equals 0, or in other words, basically du dt is equal to minus r over L u. Okay, and so now I have to basically solve this equation again, and we just actually just solved it earlier. You do the guess and check thing, right? So guess and check. Okay, u is equal to I'll call this basically be some amplitude exponent alpha t, right? And then that's my guess. And my check, plug in. So that this part is basically, this first piece is going to be alpha a exponent alpha t. So that's basically d dt of a exponent alpha t, right? That's that part. That's going to be equal to this part minus r over L of what? U, which was basically this thing, a exponent alpha t. And now we're done. That cancels that, that cancels that, and we have basically a relationship between alpha and r versus L. So alpha is equal to minus r over L. Okay, now a lot of times basically we're going to write this thing in a way that's a little simpler. This is always sometimes a little obtuse, right? We're going to write something a little clearer, right? Like this: u is equal to a exponent minus t over t tau. Okay, and tau then is equal to minus 1 over alpha here. Okay, right? Obviously, just from this look at this, these two things, right? So in that case, basically what we have, alpha is this thing. That means tau is equal to L over R. Okay, so what we have is that we have V, okay, U is equal to, defined early, V over R minus I is equal to A exponent minus T over tau, where tau was defined earlier. Tau is equal to L over R. Okay, and basically at t equals 0, I know that I equals 0. There's no current initially, right? And so that gives me that u at t equals 0, plug that in, is A, which also is equal to, at t equals 0, I equals 0, so that's equal to V over R. Okay, and so what we have is V over R minus I is equal to V over R exponent minus T over tau, or in other words, basically I, which is what we're solving for, is equal to V over R 1 minus exponent minus T over tau. Okay, all right, so if you want to plot this thing out, it looks something like this. Plot I here. Function t, it starts at 0, it comes up rapidly, and then asymptotes out at a value V over R. Okay, so it's essentially charging up, if you can think of it, charging up an inductor. Right? And tau is L over R is the time constant of the circuit. Okay, so let's try another circuit. Okay, so let's try another circuit. Okay, so I'm going to draw the following circuit here. Here's my battery. I'm going to make this thing pass through. Okay, and I'm gonna have a different circuit here. So first I'm gonna basically charge this thing up. So I'm gonna flip the switch down. It's gonna charge this entire thing up. Okay, so at t equals minus infinity, battery is connected. Okay, so it's connected. This thing's charging up. Okay, and then at t equals 0, I'm gonna flip to B. So I'll call this A, B. I'll flip to B. Now this circuit is going to be activated, and at t equals 0, there's going to be some current flowing through this, right? So what's the current? Well, initially I know what it is, right? So if at t equals by infinity, I flip it on. After a long period of time, the amount of current flowing through it will be V over R. So basically, in this case, I at t equals 0 is equal to V over R. All right, and I'm going to basically try to understand what happens to the circuit afterwards. Right, so I'm going to flip it and take a look. All right, so in order to do this, let's do Kirchhoff's law again. So start here. I'm going to flip this thing. Let's go around. So I get basically a minus IR going around again, minus L di dt. Okay, again, I'm going to assume now this current is flowing this direction. That's I. Entire thing equals 0 now. Okay, so let's go ahead and compute this thing out. Let's first copy this thing down first, right? So minus IR minus LDI dt equals 0. All right. And again, basically, you can solve the same way. So solve as before. Let's guess and check. Like the guess is going to be equal to a exponent minus t over tau, right? And so if you do as the same before, like you guys do it, tau is just going to be equal to L over R, all right? And A is just going to be equal to the initial A, which is V over R, which is just I, t equals 0. Okay, so now basically if we do that, right, what we have is I is equal to V over R exponent minus t over tau, right? And let's plot what that looks like now. Okay, I, t, and it just basically starts out here, V over R, and it comes falling down rapidly like that. Okay, so this is a discharge of circuit. Okay, all right, so now we're going to be left with one final thing, all right, which is going to be self-inductance and magnetic energy. All right, so let's go ahead and talk about that. Okay, so let's discuss. Okay, how I want to say this. Right, self-inductance. This is self-inductance. So okay, anyway, so I should say first. So the thing that we dealt with thus far, this inductance thing, is really self-inductance, right? Okay, and we're going to talk a little about mutual inductance in a second, right? So let's talk about self-inductance. Of a toroid. So let's imagine I have a toroid now. Okay, so what's toroid look like? So the donut, all right? And I'm going to make it a little simpler than normal. Let me think. Well, let's just do it then, all right? Here's my donut. Okay. Let me think about this. I think I want to make it like this. I'm going to make a square first. Go around, come back. There's another square here. Close that up. There we go. There's my little donut here, right? And it has two radii, radii A and radii B. Okay. Okay, so the first thing we'll do is basically use Ampere's law to get the B field, and then from that we're going to compute out what the magnetic flux is going to be. Okay, so basically the strategy is Ampere's law to find B field, and then number two is going to basically compute the flux, magnetic, and then number three is that we're going to then basically get the inductance then. Find L, right? So very similar three-step process to use for calculating capacitance, right? So okay, step one, right? So Ampere's law. So Ampere's law, integral C B dot dl is equal to mu 0 times I going through that piece there, right? So again, basically if we do this carefully, we cut this thing down and take a top-down picture of this thing. So we look at it. Let me just tell you first of all that there are n turns here, okay, and then there's some current I flowing through everything. All right. And in order to do this thing correctly, I believe I need to know the height of this thing. So that'd be some h. All right. Okay, h won't become important until a little later, right? So let's take cross section of this thing. If I take cross section of this thing, so it's going to be moving in on the inside, okay, A, and then moving out on the outside. This is B, all right? And I need my curve. There's my curve right there. This is C, and it's going to be a radius, a circle radius R. All right, so if I do this thing, all right, you argue the symmetry issues, basically will sort itself out. This is 2 pi R. Okay, again, easy hard. 2 pi R times B is equal to mu 0. How much current is contained here? Let's count them. Well, there are n turns, and every turn has I moving through it, so it'll be n times I. Okay, and so we're left with B field is equal to mu 0 Ni over 2 pi R. Okay, which is what we got before. Okay, perfect. Okay, so now let's get the flux of the coil. All right, so that's part B now. Part 2, phi sub m is equal to integral of B dot dA is equal to, well, now we're going to assume it's roughly uniform. It's going to be basically be B times H. Okay, we'll split them into tiny little segments. Each one will be dr in width and h in height. So in other words, basically we write this as h dr. Okay, and so if we go ahead and do this now, this is just going to be equal to mu 0 n I 2 pi r, put the integral here, there's h dr. Okay, so almost everything is constant except for these two pieces, and we're integrating from r equals a to b. Okay, so this is going to be equal to mu 0 n I over 2 pi h integral of 1 over r dr. This is the natural log of r. Okay, so this is going to be equal to mu 0 n I over 2 pi h natural log of r evaluated at r equals a to b. Okay, so let me just capture that for you. Okay, so now the key is that natural log of R A to B is natural log of B minus natural log of A, which is natural log of B over R, right? Just a consequence of basically how this stuff works. So now we're just done. Mu 0 n h over 2 pi natural log of b over a. Now I haven't forgotten the I, okay? I'll put the I out here. The reason why then is that this thing becomes the inductance L, and this is just I associated with it. Okay. So, okay, hold on. Right. Okay, so now this is the inductance through one coil. Okay, this is one coil. Okay, so for n coils, I have to multiply this times n, or add n of them together, right? So for n coils, phi sub m is equal to mu 0 n squared now, h over 2 pi logarithm of b over a times I. All right. And now, so basically now we have L. This object here is L now. So L is equal to phi m over I, which is mu 0 n squared h over 2 pi logarithm of b over a. All right. Beautiful. Okay. So now what we've done is that we consider self-inductance. All right. So self-inductance is that object generates its own B field, right? But we can also get basically flux from another object. Okay, so for instance, if I have object basically 1 here, and this is generating some B field. This can basically also go through object 2, right? And basically generate a current here. So in this case, this is called mutual inductance. Okay. So phi, the magnetic flux, right? From 1 on 2 is equal to the mutual inductance of 1 on 2 times I of 1. Okay. So this is the mutual inductance of 1 on 2. All right, and this is current of I, current on loop 1. Okay. All right, and so the mutual inductance is equal to the mutual inductance is equal to the magnetic flux from 1 on 2 divided by the current through loop 1. Okay, so here's an example. Okay, suppose you have 2 solenoids There's one solenoid here. There's another solenoid here. This one is solenoid number 1. It has N1 turns. This solenoid number 2 has N2 turns. Right? And so basically we know what the B field for solenoid 1 is. The B field for solenoid 1 is just going to be basically mu 0. Let's give this thing a length L here. Right? N1 over L times I1. Right? So basically the flux from 1 on 2, well, that's just going to be equal to, well, there's N2 turns here, right? Each turn has A2 stuff, and there's a B field here, and the B field will be from the solenoid 1, right? So this is going to be equal to N2 A2 mu 0 N1 over L I1, right? Okay, now we're going to basically say the area is the same, so just be A here. So then basically M12 is equal to phi of M1 on 2 divided by I1, so that's going to be equal to basically N2 let me get this right, A mu 0 N1 over L, okay? And in other words, basically if these two are the same length together, then this is just going to be basically equal to mu 0 N1 N2 L times A, where N1 is N1 over L, N2 is N2 over L. Okay. Right. Now, this would be the same. If you do the same analysis, right? If you did same analysis on 2 to 1, you also get basically M21 is equal to mu 0 N2 N1 L times A, right? So I just flipped everything here, right? And so what that tells you is that M12 equals M21, which is equal to some mutual inductance M, right? Okay, so the mutual inductances basically give you the same result. All right. Okay, so the last thing I want to discuss here is the magnetic energy. And look at that, I'm down to my last sheet of paper. Okay, so let's talk about the magnetic energy. All right. So let's set up that circuit again that we started out with. So here's my circuit. Okay, this is some V, some R, some L. Okay, and then some I flows around this way. So V minus IR is equal to minus L di dt equals 0, right? Kirchhoff's law again, right? And so what I want to do here is I will multiply by I. Right, so that's going to be VI minus I squared R minus Li di dt equals 0. So what is this? This is the power. This is the power dissipated by a resistor. And so thus, this must be some power that's stored in the inductor. I'll call it basically dum dt. Okay. And so basically what you have is that dum dt is equal to Li di dt, which implies that u of m is equal to Li squared with a 1/2 in front, right? So this is the magnetic energy. In inductor, right? Now for a solenoid, B is equal to mu 0 n times I, right? Which implies that I is equal to B over mu 0 times n, right? And L is equal to mu 0 n squared times A times L, right? Which implies that um is 1/2, plug everything in now, mu 0 n squared A L. Now let's put the I squared here. This is B squared over mu 0 squared n squared. Okay, so let's basically compute this thing out now. So that kills that term. This kills one of those terms. And you have something pretty simple now. Um is equal to 1/2 B squared over mu 0, and this is A times L, right? So there's, this thing has a different part. This is the area times the length of a solenoid. It's cross-sectional area times the length, which is the volume. And this thing here, this thing is the total energy. And so this is the energy density, right? Because it's density, any density times the volume is the total object, right? So little u of m is 1/2 B squared over mu 0 is the energy density, okay? Compared to big U, which is the total magnetic energy. Okay, and that's it for now.